Hi team, we are ready for 4.3, one-to-one and inverse functions. Well, let's first define what a one-to-one function is. Not only is every input mapped to only one output, that makes it a function. So it has to be a function first, but then every output is also mapped to only one input. Okay, so it's a monogamous relationship. So you may recognize these three graphs. We talked about these three when we're looking at a function. This first graph is definitely a function. Every x value is mapped to only one y value. But if I picked a y value, say like 2, notice it has 3 different x values mapped to that one y value. So if we were to pass a horizontal line through that graph, it would hit the graph at more than one point. So this guy is a function, but not one-to-one. Our second graph is a line. And again, this line, this linear equation here was a function. Every input x had only one output y. But you would also notice that if I were to pick any y value, let's say -2, it is mapped to only one x value. So if we were to pass a horizontal line through this graph, it would hit the graph at one point at a time. So not only is this a function, but this is a one-to-one function. Our third graph, the circle, if you remember, is not a function at all, because if I were to pick an x, let's say 1, it hits the y twice. So it has to be a function first before we check to see if it's a one-to-one function. So we don't even need to check here. But it wouldn't pass a vertical line test nor a horizontal line test. So this guy is just not a function at all. So again, vertical line tests if it is a function. Okay, got to do that guy first. A horizontal line tests if it is a one-to-one function. Okay, but again, it must pass the vertical line test first. Has to be a function first. Now, if graphs are one-to-one, we can look at their composition of each other. Let's say we had two functions f of g, f and g. If we took f of g and got x back, and then reversed it and took g of f and got x back, then f and g are said to be inverse functions. Now, a quick recall, remember the composition of functions means if we had f and we plugged in the g function into it, and then if we had the g function and plugged in f into that. So you have to do it both ways and get x back or your input variable, whatever it is, every single time. So just like we have inverse operations, addition, subtraction, multiplication, and division, we also have inverse functions. The notation for an inverse function is f with a -1, looks like an exponent up here, superscript of x. Do not confuse it with reciprocal, okay? So you have to look at the context. If that -1 up there in the exponent position is within a function notation, then it is in fact an inverse function of the parent function of f of x. You do not flip it. One interesting thing about inverse functions, if f of x has the point, let's say AB, its inverse function will have the point BA. I love having questions like that on like a test or a graph. Let's say down here, if I said, if f of 3 equals 10, I would ask you to find one point on f inverse. Well, if this contains the point 310, then f inverse would contain the point 10.3. It's a real easy point or two on a test, but a lot of people miss it. But this is a basic foundation here. And also remember, a function must be one-to-one in order to have an inverse. So one of the things that we can do is we can restrict the domain to make the function one-to-one. In other words, say we're only going to define it from 0 to infinity to keep it a one-to-one function. Okay. And the very last piece of information is their graphs are reflected about the line y equals x. So a couple of things. This piece of information up here at the top helps us to verify if two functions are inverse functions. And this piece of information here helps us to find an inverse. And we'll do some examples down below.